Hello friends, welcome to my channel. Let's have a look at the newly appeared problem, that is problem 2385, amount of time for binary tree to be infected. So in this video, we're going to share a format of solution based on breadth-first search. So let's first look at the statement of the problem, which is actually very short. So we are given a root of a binary tree with unique values. So notice here, unique values. So this can be important for this problem. And an integer called start. At minute 0, an infection starts from the node with value start. Then each minute, a node becomes infected if its neighbor actually was infected. So as specified here, the node is currently uninfected and the node is adjacent to an infected node. So we are required to return the number of minutes needed for the entire tree to be infected. So here is example 1. So in example 1, so initially the node 3 is infected. Then actually after 4 minutes, so all the tree nodes are infected. So the output is 4. So you can see the explanation. So in example 2, so actually the tree contains a single node, that is the root itself, and it was infected. So the output is 0. So before we write the code and do the analysis, let's first look at the constraints. First, the number of nodes in the tree is in the range 1 to 10 to the power 5. So 10 to the power 5 actually is a decent large number. So secondly, the node value is also in this range. So and the third one is that each node has a unique value. So this actually is important. So because for our solution here, we're going to build a graph in order to get the neighbor node relation easily. So a node with the value of start exists in the tree. So this is actually an consistency assumption. So with that said, let's look at the method. So the method actually is very routine. So we're going to use breadth-first search because it's actually related to shortest distance. So breadth-first search comes into play here. So the idea is straightforward. So we're going to do breadth-first search from the given source start, and then we read it out layer by layer until all the nodes are infected. So in the process, we just need to count the number of layers. So this is what we need to return. So another thing that is important for us is that in order to do node-neighbor relation or get the relation easily or fast, so we could build a graph for convenience. So before we do the code, actually here is an extension or connection. So it might be beneficial to look at the tree diameter problem or longest path passing a given node. So this kind of problem are actually connected or related with the problem here. So in particular, you can have a look at Leetcode 543 or corresponding videos in my channel. So now let's look at the code. So we are going to do it step by step, and in between give a line by line explanation. So first, let's do this. So let's build a graph. So this actually is not absolutely necessary for this problem, but building the graph provide us some convenience to get node-neighbor relation. That is, aid us to do the breadth-first search. So for this, let me initialize a variable called graph, the collection's default dict. So I'm going to use that as the container to hold the neighbors of a given node. And then we're going to do a traversal. So when we do the traversal, we're going to actually build the node and parent relation. Right. So for this, I'm going to write a hyperfunction. So and then I'm going to call the function directly. So here, let's call this function traverse. So because essentially it's a traversal of the tree. So starting from root, first, if not root, so we're going to stop or return. So you can think of this traverse as a worker. So next we're going to initialize a stack, so which contains the root and none. So here, in other words, the tuple stars node and parent relation, right? So then we're going to do the traversal, or which is a standard while loop, while stack. Then we're going to get the node and parent. So that is stack and pop. So in other words, we are actually doing depth first search. So because we're using stack. So in order to incorporate with this tree data structure, actually we will first look at the right child and then left child. So first, if parent is not a none, in other words, if the node is not the root node, so we're going to do things like this: graph, so parent value, then add, so the node value. Actually, the relation is two-sided for the graph because we want to compute the sort of diameter, right? So we also need to add node value, add a parent value. So in other words, the node is a neighbor of the parent, and the parent is also a neighbor of the node. So in the building of the graph, so this assumption that each node has a unique value plays an essential role, right? So once this done, so we're going to check if node right. So notice here I'm first adding the right subtree. So I'm going to add the node right and node. So in order to preserve the node and the parent relation. And if node left, so I'm going to copy this one and change the right to the left. So this way, actually, we finished building the graph. So then what we do actually is we call traverse for the root. So this way, actually, up to now, we have a full-fledged graph which encodes the relations inherited from the tree represented by the root node. So next step is to do a breadth first search to locate the number of minutes needed to make all the tree infected. So step 2. So breadth first search. So for this, actually, we can also first define a hyperfunction and then prepare the return. So first, let's define the breadth first search function from the source. The source is going to be the start given in the problem. So let's use the source as an argument here, just for clarity. So here is a single source breadth first search hyperfunction. So let's first initialize a result variable that is 0. So whose final state is what we need to return. Then we're going to initialize a set called visited. So this actually is used to aid the breadth first search. In other words, avoid repetition. So with that said, because we are doing breadth first search, we're going to use a queue. So actually here I would prefer to use a deck container to mimic the queue behavior. So first I'm going to add the source and 0, because the source to itself actually has 0, or you can regard that the source is layer 0, and then the neighbors is layer 1, and the neighbor of its neighbor is layer 2, right? So here what we store is the source or layer number or distance, if you like. So with that said, we are ready to do the traversal. So that is while q. So we're going to first get the vertex as a time or layer or something as we. So we are going to use time because here the problem interprets this layer as time or minutes. So let's call q pop left. So and then we're going to check. First, let's update the result. The result will be the maximum of the previous state and the current time. And then we're going to look at the neighbors. So if vertex not in visited, right? So if this is the case, so we're going to add this to vertex to the visitors. Actually, we do not need to use this if. If in the below check, we check if the neighbor is invisited or not. But let's keep this format. So for neighbor in graph vertex, right? So then, as we mentioned here, if neighbor not invisited, so we're going to include this neighbor, and the layer or the time should be the previous time plus 1. So that way, after the queue is empty, so actually we get the largest layer number. So that's the thing we are going to return. That is the result. So once we done this hyperfunction, then we can call this function and return the final result. Let's do the return BFS. So we're going to put a start here, right? So that's actually the full solution for this problem. Let's first do a special case check. Yeah, it passes example 1. Now let's do a generic case check. Yeah, it passes all the test cases. So let's give a quick summary to end this video. First, actually we built this graph in order to easily access the node and neighbor relation inherited from the root. And secondly, actually we did a breadth-first search. So essentially, this problem actually computes a sort of shortest distance. That's why the breadth-first search comes into play. In this step, also we write a hyperfunction and then call the hyperfunction to get the final result. So that's the code structure. So here are some further information like we remarked at the very beginning. So it might be beneficial to look at the tree diameter problem or longest path passing a given node. So another remark may be that, so this is one format of solution to this problem. So you can actually devise other code formats to solve this problem. So with that said, I guess that's about it for this video. Thank you very much.